So far in this course on statistical inference, the portion for which I have covered the testing of hypothesis, I have considered two major approaches. One is the theory of most powerful test, uniformly most powerful tests or uniformly most powerful unbiased tests, etcetera. The theory which has been developed following Neyman-Pearson's work. And we derived the exact test for several situations, especially for the parameters of the normal distributions. The another approach which I considered was the consideration of likelihood ratio test, and there also we were able to derive the exact test for various situations. One important point which I mentioned in the likelihood ratio test is that sometimes when the exact distribution of the test statistic in the likelihood ratio test is not possible, the asymptotic distribution of minus twice log of lambda, where lambda is the likelihood ratio, is a chi-square distribution under the null hypothesis, and that is helpful. Now, today we will discuss another type of tests. Many times we are saying we want to test whether the data comes from a particular distribution. That means, whether the data is from binomial distribution, whether the data is from a Poisson distribution, whether the data is from an exponential distribution, etcetera. And then how to test that. So, a class of tests for this has been developed, they are called goodness of fit tests. However, I will restrict attention to only chi-square tests for this situation. So, the model is like this. Suppose we are having a random sample from a population, say f x. Okay. Now, this f x may depend upon a parameter, it may not depend upon a parameter. So, may depend upon a parameter theta. In the non-parametric situations, we may not consider this theta here. Now, we want to test hypothesis, say f x is equal to some known distribution f x for all x against not equal. So, that means, for at least some x. Now, there can be two cases. I am considering case 1, f naught is completely specified. Now, we want to test whether the data x 1, x 2, x n is actually from this distribution f naught. Okay. So, the method of applying this chi-square test for goodness of fit is the following. We classify, or you can say we divide the range of the distribution f naught into k mutually exclusive and exhaustive intervals. Okay. Let us say these intervals, say j 1, j 2, j k. That means, what we are saying is that these j i's are disjoint and the union of j i's is the range of the variables, that is the range of the distribution. Suppose it is from 0 to infinity, or it is from minus infinity to infinity, or if it is a finite interval from a to b. Now, the theoretical probability of interval j i, that is probability of x belonging to j i, is equal to say pi I is equal to 1 to k. Let us consider, say So, when we are considering the observations divided into intervals j 1, j 2, j k, then there will be observed frequencies. So, let O 1, O 2, O k be the observed frequencies of j 1, j 2, j k. Okay. Then the vector O of this observed frequencies O 1, O 2, O k has a multinomial distribution. We can write it like this: probability of say O 1 is equal to small o 1 and so on, O k is equal to small o k, that is equal to n factorial divided by product of O I factorial, I is equal to 1 to k, then product of pi I to the power O I is equal to 1 to k, where sigma of O I is equal to n and sigma of pi I is equal to 1. Now, expectation of say O I, that will be equal to n pi I, let us call it say E I, and variance of O I, that will be equal to n pi I into 1 minus pi I. In the multinomial distribution, these are the statements that are satisfied. Now, let us take say k equal to 2, that means only 2 classifications are there. Then actually it becomes binomial distribution, and for binomial distribution we have the statement x 1 minus n pi 1 divided by square root n pi 1 into 1 minus pi 1. So, this x 1 is O 1, this converges in distribution to normal 0 1. This is the notation for convergence in distribution. The asymptotic distribution of O 1 minus n pi 1 divided by square root n pi 1 into 1 minus pi 1 is standard normal. This is by the binomial approximation to the normal distribution. Now, this implies that if I consider O 1 minus n pi 1 square divided by n pi 1 into 1 minus pi 1, then the asymptotic distribution of that will be chi square on 1 degree of freedom. Now, for k equal to 2, we will have O 2 is equal to n minus O 1. So, we can then show that O 1 minus n pi 1 whole square divided by n pi 1 plus O 2 minus n pi 2 whole square divided by n pi 2, that is equal to O 1 minus n pi 1 square divided by n pi 1 into 1 minus pi 1. That is the distribution of O I minus n pi I square divided by n pi I is equal to 1 to 2, that is asymptotically chi square 1. For general k, we can proceed in the same way. We can show that the distribution of O I minus n pi I square divided by n pi I is equal to 1 to k is asymptotically chi square on k minus 1 degrees of freedom. Now, when so this pi i's are the theoretical probabilities, we calculate this E i's, that is equal to n pi I from the known distribution f naught x, okay, that is under h naught. So, this expression then becomes, then this T is equal to sigma O I minus E I square divided by E I is equal to 1 to k. This is asymptotically chi square on k minus 1 degrees of freedom. So, we can set up a test for goodness of fit by reject h naught if t is greater than chi square k minus 1 alpha, where chi square k minus 1 alpha is the upper 100 alpha percent point of the chi square k minus 1 distribution. Now, here you have some sort of simplification also available. In place of this, see this we can write sigma O I square plus E I square minus twice E I divided by E I, that is equal to sigma O I square by E I plus sigma E I minus twice n twice O I E I. So, that is equal to minus twice O I sigma. Now, sigma O I is n, sigma E I is n, that is the total number of observations. So, that is equal to sigma O I square by E I plus n minus twice n, that is equal to sigma O I square by E I minus n. So, this is a simplified formula for T here. Let me give an example here. A random variable simulator is used to generate 1000 values for a uniform 0 1 random variable. The values are classified into intervals like 0 to 0.1, 0.1 to 0.2 and so on, 0.9 to 1. Okay. The observed frequency distribution is as follows. So, here I will present interval and here the number of terms. So, these are O i's between 0 to 0.1, between 0.1 to 0.2, between 0.2 to 0.3, so there are 1 1 2 values here. Between 0.1 to 0.2 it is 101, 94, 0.3 to 0.4, 99, 0.4 to 0.5, 108, 0.5 to 0.6, 93, 0.6 to 0.7, 94, 0.7 to 0.8, 100, 0.8 to 0.9, 104, and 0.9 to 1, there are say 95 values. So, we want to test whether the simulator is working properly. So, what does it mean that the simulator is working properly? If it is working properly, then the observations that we have got and we have classified like this should fit into a uniform distribution on the interval 0 to 1. That means, we want to test the hypothesis whether f x is equal to say u x, where u x is CDF of uniform 0 1 distribution, against the hypothesis not, that f x is not u x. So, in order to apply the chi-square test for goodness of fit, I need to calculate the probabilities of the intervals. Now, if I am assuming under H naught probability of this each interval of this nature, that is 0 to 0.1, this will be 0.1 and so on. Probability of each interval 0.9 to 1, that will also be equal to 0.1. That is, these are my pi i's. So, pi i's are 0.1 for I is equal to 1 to 10, that is k is equal to 10. We are having 10 classes here. Now, based on this ei is equal to n pi I, that is equal to 1000 times 0.1, that is equal to 100. That means, for each class in this case ei is only 100. So, if we want to apply this chi-square test, I need to calculate sigma o I minus E I square by E I, or I can also calculate sigma o I square by E I minus n. So, these things are not difficult now. This t statistic then, so the test statistic t, that is equal to 112 square by 100 minus 101 square by 100 plus all the terms will be plus 95 square by 100 minus 1000. Now, this can be easily evaluated. This value turns out to be 3.72 approximately. Now, we need to look at the value of chi-square on 9 degrees of freedom at alpha level of significance. Now, you can see the tables of chi-square distribution. So, I will show from here. So, tables of chi-square distribution, suppose I look at say 0.05, the value is equal to 16.91. So, chi-square 9 on 0.05 is say 16.91. We may also look at say chi-square 9.01, that is equal to 21.67 and so on. So, these values you can see they are larger. So, H naught cannot be rejected. That means, this simulator seems to be working properly. Now, in this particular case, when I wanted to test whether f is equal to f naught, then f naught was completely specified, because I said uniform 0 1. But there can be cases when the distribution may be known, but it may not be completely known. For example, it may depend upon a parameter. Suppose I say uniform 0 theta, or I say binomial n p, where p is not known. So, I want to test whether the data is from a binomial distribution, whether it is from a normal distribution, but the parameters may not be specified. In that case, we need to actually estimate those parameters from the data. So, I will consider case 2. F naught is not completely specified. For example, it may consist of say S parameters. If it consists of parameters, then these probabilities need to be estimated. So, what we do? So, in this case, we first find say maximum likelihood estimators of parameters to get estimates of pi I theta, say pi I head theta. Okay. Then E I head, that is equal to n times pi I head theta. So, I am just writing n pi I head. Now, let me say W, that is equal to sigma O I minus E I head square by E I head, I is equal to 1 to k. This has asymptotic chi square distribution on k minus 1 minus s degrees of freedom. So, in place of k minus 1 now, it is becoming k minus 1 minus s, because this is the number of the degrees of freedom which are now reduced because of allocation, or you can say estimation of the parameters which were unknown. Let me give one example of this situation here. So, we have the data say on certain arrivals. Okay. The number of arrivals at a service counter are assumed to have a Poisson distribution. Okay. The time period is over hours. Okay. Now, the following data is recorded on a particular day. So, the no arrivals were observed 22 times on a particular month, let me say, sorry, in place of day, and one arrival was observed on 53 times, 2 arrivals were observed 58 times, 3 arrivals were observed 39 times, 4 arrivals were observed 20 times, 5 arrivals were observed 5 times, and 6 arrivals were observed 2 times, 7 arrivals were observed 1 time. So, the total data was 200. Now, when we apply the chi-square test, the expected frequency for each class should be greater than or equal to 5. If it is below that, then we need to combine. Now, here you can see the observed frequency for these two classes is less than 5. Naturally, when we consider the estimation, it may turn out to be less. So, what we do? We merge this. We merge this into one group, say 8, and now we do not know the parameter of the Poisson distribution. So, we estimate lambda by the mean. So, we consider 0 into 22 plus 1 into 53 and so on plus 1 into 7 divided by 200, that is approximately 2. So, then expected frequencies are calculated using the probability distribution. So, we have e to the power minus lambda, lambda to the power k by k factorial, k equal to 0, 1, 2 and so on. So, what is the probability x equal to 0? That is e to the power minus lambda, that is equal to e to the power minus 2. So, this is O I, this is E I. So, E corresponding to the first grouping, that is equal to 22 into e to the power minus 2. So, this can be calculated. Then we are having probability x equal to 1, for example, that is equal to lambda e to the power minus lambda, that is twice e to the power minus 2. So, E 2 then will become 53 into 2 e to the power minus 2, that is 106 e to the power minus 2. Similarly, you can calculate probability x equal to 2, say, that is equal to lambda square e to the power minus 2 by 2 factorial, that is equal to again 2 e to the power minus 2. So, E 3 that will be equal to 58 into 2 e to the power minus 2. Similarly, you can calculate, say, probability x is equal to 3 and so on. And I will combine these three probabilities, that is, you can consider them as probability x greater than or equal to 5, and these values will then turn out to be sorry, this is slightly mistaken here, this should be 200 here, you have to multiply by n. So, this is 400 e to the power minus 2, this is also 400 e to the power minus 2. So, now let me write down the values here, these values are 27, 54.2, 54.2, 36, 18, and this last 3 we add up, it is 10.6. This total is again 200 here. Now, we calculate this sigma O I minus E I square by E I. This can be calculated, it turns out to be 2.33. Now, let us compare from the chi-square value on how many groups we have made. We have made 5 groups, that is 0, 1, 2, 3, 4 and greater than or equal to 5. So, there are 6 groups here. So, we look at the chi-square value on 5 degrees of freedom, and this value then turns out to be 11 point, say 0.05, it is 11.1433. So, once again we can say that H naught, that is the hypothesis that the data is from Poisson distribution, cannot be rejected. Now, this chi-square test for goodness of fit has some further generalizations, or you can say further applications. Let me give the application of it for testing for independence in a contingency table. Earlier you remember that when we were discussing the theory of UMP unbiased tests, I considered a 2 by 2 contingency table, and I actually obtained an exact UMP unbiased test. However, that UMP unbiased test was depending upon certain discrete distribution, and so it was not very convenient to apply. You need to look at the tables, and moreover it is a discrete distribution, therefore, the randomization will be required to get the exact level of significance there. However, if we consider the large sample test, actually it is a chi-square test. Let me give this thing. So, testing for independence in R by C contingency tables. So, contingency tables are used when the data is categorical, and so for example, you may like to test whether the selection of say students in a particular entrance examination dependent upon their financial status, or you can say the financial status of their parents, or is it dependent upon the educational status of their parents, or is it dependent upon the level of the schools where they are studying, the school board, and so on. So, on one side you have certain category, let us say A1, A2, AR. On the other side you have category B, which is having say C classifications. Okay. So, this is attribute A, this is attribute B. Suppose a population is categorized according to two attributes A and B. Say for example, A is the income level. So, we may say A has say 4 levels, say A1 is high income group, say HIG, A2 is say upper middle income group, that is say UMIG, then A3 is say lower middle income group, LMIG, and say A4 is lower income group, that is say LIG. So, I am distributing, or you can say dividing the population into 4 groups according to the attribute which is income level, and second one is say expenditure on say education, and then again I put B1, B2, B3. So, this is say more than normal, average, and below average. I consider, so this is A, this is B. Now, A1, A2, A3, A4. On this side you have B1, B2, B3. Okay. I consider say a random sample of say 1000 individuals. Out of the 1000 individuals, how many fall into each category? How many fall into each category? So, there are say 12 classes here. I am just creating an hypothetical data here, say 78, 112. So, this is say, let me put here 3 classes are there. Let me put some rough numbers here, say 330, 340 and say 330. This is just incidental, I am fixing the values in some way, so that the totals match here. So, this is 190 plus 110 say 30, 80, 110 and say 100, 40, say this is 85, 105, 95, so this is 140, this is 50 here, this is say 90, sorry. So, these totals will add up here. Now, we want to test whether there is a relation or you can say association between the two attributes. Can you say that if the income is high, the expenditure on the education will be more, or if the income is low, then the expenditure on the education will be less, and so on. That means, is there a dependence on this? So, we want to test this. You can see this is called a categorical data. Categorical data as opposed to the numerical data that you have in the other problems. Now, for this we can create the situation like this. So, I am making a general setup. You have observed frequencies, I will call O11, O12, OR1, O1C, ORC. These are the OIJ is the observed frequency of the ijth cell. So, this is n here. Now, I have considered a random sample of size n. A random sample of size n is taken from the population. Okay. Let us consider, say, let pi I j be the probability of the observation belonging to ijth cell. Okay. Our null hypothesis is that row and column attributes are independent, and our alternative hypothesis is that they are not independent. Okay. So, we write down the totals here, pi I dot, that is equal to sigma pi I j, j is equal to 1 to c, pi dot j, that is equal to sigma pi I j over I is equal to 1 to r. So, pi I dot is the probability of observation belonging to the A I, and similarly pi dot j, this is the probability of x belonging to B j, okay, and pi I j is probability of x belonging to A I intersection B j kind of thing. Okay. So, the hypothesis of independence is then equivalent to that pi I j is equal to pi I dot into pi dot j for all I j. Now, the if independence is there, expected frequency of I jth cell, that will be equal to n times pi I j. Let me call it E I j. Okay. So, then we can say that O11, O12 and so on, all of this taken together, this has a multinomial distribution with cell probabilities pi 11, pi 12 and so on, pi r c, and sigma of pi I j, I is equal to 1 to r, j is equal to 1 to c, that is equal to 1. So, by the goodness of fit explanation that I gave earlier, if I consider double summation O I j minus E I j square divided by E I j, I is equal to 1 to r, j is equal to 1 to c, will have an asymptotic chi square distribution. Now, how do you evaluate these things? Since the theoretical values are unknown, that is E I j's, that is pi I j's are unknown, we estimate them okay. How will you estimate that? You can consider say R I, that is equal to sigma O I j, that is the totals on the row side. If I add here, I call it R 1 and so on, R R, and on this side if I add, I call it C 1, C 2, C C, that is the row totals and column totals. J is equal to 1 to C, and C j, that is equal to sigma O I j, I is equal to 1 to R. Okay. Now, pi I dot, that is the estimate of the ith row probability, row attribute probability, that can be estimated by R I by n. This is the maximum likelihood estimator of pi I dot. Similarly, if I consider pi dot j head, that is C j by n. Okay. This is the maximum likelihood estimator of pi dot j. So, we can consider E I j head as equal to R I into C j divided by n into, so here divided by n and here divided by n and then multiplied by n. So, that n will cancel out, I can write just this thing. So, this is MLE of E I j. So, how many parameters we are estimating here? This total is having R c classes. So, we will have the degrees of freedom R c minus 1. Okay. This will have on R c minus 1 degrees of freedom, but now we have estimated R plus c terms. Okay. Since we have estimated R plus C parameters, the degrees of freedom for chi square will be R C minus 1 minus R minus C, that is equal to R minus 1 into C minus 1 here. I think I have made one error here. This will become R C plus 1 minus this one. So, asymptotic distribution of, say, let me call it chi W star, that is equal to double summation O I j minus E I j head square by E I j, I is equal to 1 to R, j is equal to 1 to C, that will be asymptotically chi square on R minus 1 C minus 1 degrees of freedom. This is actually minus 2 here. The reason is that the total is going to be 1. We are getting sigma pi I dot is equal to 1 and sigma pi dot j is equal to 1. So, the last two parameters are not estimated. Okay. So, we have estimated R plus C minus 2. So, this is R C minus 1 minus R minus C plus 2, that is R minus 1 into C minus 1 here. So, asymptotically this will have this distribution. So, the test is to reject hypothesis of independence if this W star is greater than chi square R minus 1 C minus 1 alpha. Now, there is yet another situation here, because here in this particular case what I have considered, the total sample size for the population was fixed like n. Therefore, each of this O I j's, these became random variables, these are also random variables and therefore, they had multinomial distributions. But there can be another situation, for example, the population may be large, therefore, we may not fix the total sample, rather we may fix the sample according to the categories. That is called testing for the homogeneity in a contingency table. It could be like this. For example, we may like to, we have a distribution of people having different diseases. Okay. Now, we categorize the population according to different ethnic groups. So, for example, we are considering say Asians, we may consider say Caucasians, we may consider say say Africans and so on. Now, we look at that whether in those populations the distribution of the diseases, various diseases is the same or not. But in place of taking the random sample of from the total population, we consider a certain number from say Asians, certain number from Africans, certain number from Caucasians and so on, and then we look at the classification among that. Therefore, now this RIs or CJs will not be random, but the individual entries will become random. So, the setup will be slightly modified. However, we will show that the test statistic is still same. So, contingency tables with one margin fixed. This is called test for homogeneity. So, here we are considering, suppose independent random samples of sizes R 1, R 2, are R, they are taken from R populations, say A1, A2, AR respectively. In the earlier case, I have considered the full population, and then the categories were called A1, A2, AR, and according to the other attribute B1, B2, BR. Now, here from each of them I am considering the samples. So, these will be called populations, and after the sample is taken, this is classified into B1, B2, that is according to the attribute B. So, classifying each sample into categories say B1, B2, BC, we again obtain R by C contingency table. So, the nature is the same, however, the interpretation of the values is different, where row totals are fixed. Alternatively, you may fix the column totals, and then and that means B1, B2, BC may have fixed sample sizes, and then you can classify each of them according to A1, A2, AR. Okay. Now, here the probability then will become conditional probability. So, probability of the various B categories within each population, they are now Pij, that we call probability of Bj given Ai, for I is equal to 1 to R, j is equal to 1 to C. And the hypothesis of homogeneity of the populations this can be written as say P1j is equal to P2j and so on is equal to Prj for j is equal to 1 to C. Now, for estimating these probabilities, we can consider P1j head is equal to P2j head is equal to Prj head, that is equal to Cj by n. This is under H naught we are considering. Okay. So, for ijth cell Eij head, this will become Ri into Pij head, that is equal to Ri into Cj by n. So, it becomes the same value which I obtained in the previous case, and therefore, the test statistic is same as W star, that is double summation Oij minus Eij head square divided by Eij. The calculation of the degrees of freedom is slightly different now. You are having C cells, and therefore, in each cell you will have each this one you will have C minus 1 degrees of freedom. So, R times that. So, total degrees of freedom will become R C minus 1. Now, in each of them you will be considering the estimated number of parameters, that is minus C minus 1. So, that is becoming R minus 1 C minus 1. So, it is the same degrees of freedom. So, this test statistic is the same as the previous one. So, what we are observing that testing for the independence in a R by C contingency table, we are getting a asymptotic chi-square test, and the test is similar when the interpretation of the, or you can say the sampling scheme is slightly modified. In place of taking the sample from the full population, I distribute it into the stratum, and then in each strata I take a fixed sample size. However, the testing procedure does not get modified. When I discuss the various problems on the testing of hypothesis, I will discuss the applications of these two procedures which I have described today. In the following lecture, I will be discussing another important test, that is called a sequential probability ratio test. So, that I will be covering in the next lecture. I will devote a few lectures and on the problems also for various tests that we have derived in this particular course.